ECON's first event. So I'm Shao Mo. I'm an associate professor at the Purdue AAE. My research is mainly on multi-agent systems and also autonomous planning systems. And I also co-directed the Center for ECON with Professor Shreya Sundram from ECE. The Center for ECON aims to create a platform for faculties, Purdue faculties, research collaboration, and also teaching coordination. So the Center for ECON has about 60 faculties from more than 11 departments across Purdue University. So actually the number of faculties, our team is growing. And you will see actually we have 5 new faculties presented their research today. And their research directions ranging from autonomy to machine learning and to robotics. So first I want to introduce you Mahsa, and he will present efficient, reliable, and interpretable decision-making for human autonomy coexistence. And Mahsa is a assistant professor at Purdue ECE, and she joined us this fall. And she received her PhD from UT Austin, and her research focuses on theoretical and foundational advancement in enabling the design of autonomous systems. And her research interests also include active learning and control, human-robot interaction, and trustworthy AI. So Mahsa, it's all yours.
Thank you for the introduction, Shao Shuai. Hi, everyone. I'm very excited to be here. So today I'm going to talk about the challenges we face as autonomous systems enter our lives and some of the ways that I've tried to tackle these challenges by providing efficient, reliable, and interpretable decision-making algorithms. Most of this work is from my PhD when I was at University of Texas at Austin. It's Professor Ufuk Topçu's lab right before coming here to Purdue, joining Purdue in the fall. So autonomous systems are coming. They are coming in different forms, and they are entering various applications around us. At one hand, we have network systems, for example, multi-agent robotic systems or smart grids or Internet of Things, where we have a number of components that are sharing information with each other, and each of them may be gathering a large amount of data. So it is very important for these systems that we can have efficiency on how they gather data and how they process that. Autonomy has also entered ground, aerial, and space navigation, where we expect an autonomous system to perform on their own for potentially extended time horizons. So it is very important that we can somehow ensure the safety of these systems, and we have ways that we can trust them. There are also applications where humans and robots are interacting with each other closely, could be in the form of human-robot collaboration or shared autonomy or social robots. And we would like these interactions to be as effective and as smooth as possible. So these are the main 3 directions that I have worked on in my research so far. My approach toward tackling these challenges is an interdisciplinary one, in particular using control, learning, information theory, and formal methods. And I can categorize the research I've done so far in 3 directions. The first one relates to joint perception and planning. If you have systems that are at the same time gathering information and trying to use that for some sequential decision-making task, how they can do this information gathering in an efficient way, and how can they do it in a way that is toward a particular task. The second direction relates to online planning for unknown, and especially for unknown and varying tasks. So this runtime data is coming at potentially high frequency, and the systems should use that into their decision-making algorithms in a way that is reliable. And the third direction relates to interpretable planning. In particular, in interaction with humans, how can we have planning algorithms that are easily explainable? So I just want to briefly go over 3 projects related to the first 2 directions, joint perception and planning and online planning in this topic. So let's start with this joint active perception and planning. Imagine we are at the aftermath of some earthquake or some other disaster where the environment has completely changed from what it used to be. And we have some rescue robots. There could be drones, there could be some rovers. And these systems, we give them some tasks. We ask them to find any survivor in this environment, let's say. There are multiple challenges here, right? One of them is that each of them has a limited sensing capability, like maybe they can just see the area surrounding themselves, or they have just limited power that they can allocate to sensing. Also, as they gather this new data, their knowledge about their environment is changing, so should their decision making. And also, this is a safety critical and time sensitive operation, right? We don't have the luxury of giving them a very large amount of time so that they can come up with a very exact map of this environment and then look for the survivors. But rather, we want them to be as quick as possible in just gathering enough data that they need so that they can find the survivors in this area. So this is where joint active perception and planning comes into play, because on one hand side, we want this efficient information gathering, and on the other hand, we want to use this information for the planning task. Now, to deal with these settings, on one hand side, we have machine learning algorithms, and they have proven to be very effective in handling large amount of data, high dimensional data, and also fusing heterogeneous type of data. And because of that, they have been very successful in doing perception tasks. On the other hand, we have control algorithms that are very good in giving us guarantees or some sort of theoretical guarantees on the behavior of the system, for example, performance of that or the safety of the system. And as such, they have been used widely in planning algorithms. Now, what is the right interface between these two so that we can have the best of both worlds? We can have this efficient data processing as well as this trustworthy decision making. So this is part of my contribution, where I propose to have some structured task representation of what this agent is trying to do, and then use that as an interface between these two modules, the perception module and the planning module. So that from one side, we can have abstract representation of data that are communicated to the planner so that it can make a decision. And on the other hand, the planner can tell the perception module what sort of information I need for this particular task that I want to do. Without going too much into the detail, let me just give you an overview of this problem setting. We have 4 elements. One of them is the dynamics of the system. We use a Markov decision process to model that. And this dynamics is known, although it could be stochastic. There's an environment model that captures different objects and different properties that could happen at every state of the environment. And the states here are discretized. And there's a true labeling function. That is labeling function, we don't have access to it, or the agent doesn't have access to it, but it would essentially tell you what properties are happening at each of these states. But this is unknown to the system. And instead, it can use the sensors with some observation model in order to learn this labeling function. And the agent also has this high-level task represented by temporal logic. And the goal of us is, given these 4 elements, how can we come up with a policy, an adaptive policy, that maximizes the probability of successfully doing this high-level task? Here is an overview of the algorithm that I propose. The blue blocks are the perception parts, the red ones are the planning aspects, and this purple one is a combination of the two. So at every state, the agent starts gathering some data, then using that to update its belief about the environment. Then it checks to see whether its belief has changed significantly or not with respect to the previous time step. If it hasn't, then it can just continue with the plan it had before. But if it has changed significantly, then it would come up with an estimation of the most probable realization of this environment, use that to synthesize a new policy, and then it would calculate the risk because of this imperfect perception it has. if the risk is low, it means that this is a good plan. It will continue according to that. But if the risk is high, then it would kind of locally diverge from the initial plan and instead do an information gathering step. This information gathering steps tries to find the most relevant information for this task and improves the knowledge of the agent, then this entire process repeats again. So the main contributions here are, we have a way to assess the risk of this imperfect perception with respect to the task. We can also come up with task-oriented information gathering strategies. And also we can have these runtime guarantees at every point in time that would tell us what is the probability of satisfying the task given the current knowledge of the agent. Let me show some of the results that we have. The first one relates to drone navigation in urban environments. We use AirSim, which is a simulation platform. We have a drone, has RGB cameras as well as depth cameras. Then every time from every view of these cameras, it gathers this depth data and generates a point cloud from that. And also it generates some semantic segmentation from the RGB data. Then it combines this data with a discretized model of the environment to come up with its belief or its knowledge about this environment, which will be probabilistic. Like with some probability, there is an obstacle in this state or not. Here is 2 runs of the system. The left-hand side, we are using a synthetic perception module, meaning that we have exactly defined the sensor models and we have access to the sensor models. And because of that, we can actually update the agent's belief in a Bayesian way. And because the models we have are accurate, this will help the agent to more quickly learn about this environment. But when it starts, it doesn't know anything. But it is trying to find some building with a flag on top of that. And here we can, on the left-hand side, see that it is approaching the building and completing the task. On the right-hand side, though, we don't have access to this exact sensing models. And instead, the robot is using those RGB cameras and the depth cameras that I explained in the previous slide. Those sensing models are very complicated. We cannot have access to them. Or at least accurately. And because of that, we use a different update for the agent's knowledge. We use a frequentist update. So it takes longer, but it's still able to complete the task. We also implemented that for the turtle bots, have both simulation and experimental settings. So we can see on the left-hand side is the simulation. Again, we have a reach avoid task, trying to reach this checkered state while avoiding the obstacles in the environment. On top, we can see how the agent's knowledge is evolving. The green parts are where it finds to be safe, so it can pass through them, but the red parts are where it thinks there's an obstacle. Similarly, on the experimental side, we can see how the belief is updating. So the important thing is that the agent doesn't know anything ahead of time, but it tries to just gather enough data to perform the task that is assigned. All right, so let's switch gears and talk about another project, which is online planning for unknown and varying tasks. So in many of the emerging applications where we have the sequential decision making, we could have some elements that are evolving. For example, we may have a human in the recommendation system whose preferences are changing over time. Or we may be working in an environment on some other planet, we don't know anything about that, and this environment could also be evolving over time. The challenges here is that we may not have access to a large amount of data ahead of time, and we may want to do everything at the run time in a way that we can ensure safety of these systems. So in this project, we asked, how can we have online algorithms for these sort of sequential decision-making problems such that they can give us high probability guarantees? So this is the overall view of the algorithm. So at every state, the agent receives some limited feedback, banded feedback for the particular state action it is in. Based on that, it tries to learn a reward estimator. And here the task is evolving over time. So every time this estimator is going to change. And then based on this new estimator, it will update its policy through an online mirror descent algorithm. And once it updates its policy, it takes another action according to that, then this entire process repeats. In order to achieve these high probability guarantees, we come up with an optimistically biased reward estimator that implicitly encourages exploration. We have this policy search using online mirror descent that adapts the policy over time. And we also prove a theoretical guarantee that is minimax optimal with high probability. So here is how the setting looks like. So if we have, for example, a human that in an episodic, that is dealing with a robot in an episodic setting, every episode the human has a different task in mind. So whenever the robot takes some action in a state, the human will give some scalar loss value to the robot, but this task will change in the next time step. So we use adversarial multi-decision process to model these scenarios. And we have this banded feedback from, let's say, human to the robot. And the goal is that we want to learn a regret that with respect to the best fixed policy in hindsight will be sublinear. And the main question we ask that differs from the previous works in this area is that how can we have these low regrets with high probability, not just on expectation? So the first step is generating this optimistically biased loss estimator every time the agency receives some banded feedback. And once we have this optimistically biased loss estimator, we can use that in an online mirror descent algorithm to update the agent's policy. So this online mirror descent algorithm tries to kind of minimize this objective, that's the combination of the loss plus the change from the type policy in the previous time step. So this doesn't want this change to be too abrupt. And even though this is a constraint optimization, we can actually do this in two-step procedure in an efficient way. And here is the main theoretical result we have. We show that if we choose the parameters of this algorithm, the learning parameter eta and the exploration parameter gamma in this way, then we can have a regret that is sublinear in all parameters of this problem, not only on expectation, but more importantly with high probability. And this will also be minimax optimal up to some logarithmic terms. And this is a work that, let me just show this one slide, and this work that I'm currently focusing on, which is a shared control algorithm where we in brain-computer interface application. So let's say we have a patient. This patient is using their brain signals to control some system. So in this project, we are focusing on jointly inferring the task and the intent that the human has in mind, plus coming up with the shared control algorithm that ensures the safety and performance of this system. So in the interest of time, I wouldn't go too much into the detail of that, but I just wanted to, at high level, mention this project. And there are three main directions that I'm focusing on in the future. The first one is that, well, we already have a lot of data and that exists. And we can use this data and sort of similar to knowledge graphs or some probabilistic graphical models to help the agents more quickly learn about the environment. So how can we incorporate this sort of structured knowledge in sequential decision-making tasks? The second direction relates to when we have multiple autonomous agents. They could be heterogeneous agents. How should they communicate with each other? What is the optimal representation to communicate with each other? And how can we have distributed decision-making plus cooperative perception between these agents? And last but not least, I really hope to work more on the social and ethical aspects of autonomous systems, because as these systems enter our lives, there will be a lot of interaction with them, and it's very important that we can have, we consider these aspects as well. All right, thank you, everyone.
Thank you, Mahsa. And we will receive your questions at the end of the panel. And
Sure.
Your research is so interesting. I just cannot stop you in the middle. And okay,
thank you.
We will go to thank you, Mahsa. So we'll go to the next presenter. Will be Junjie Qin from Purdue ECE. Junjie is also assistant professor at Purdue ECE. And before joining Purdue, he received his PhD from Stanford and also postdoc from Berkeley. Junjie's research mainly focused on electric energy system and transportation networks. He had got award, many nice awards like Hugo Best Paper Award and also Best Student Paper and the Intelligent Transportation. Okay, Junjie, all yours.
Right. Could you guys hear me? Okay. So thanks for the introduction and thanks for the invitation to this wonderful event. I really appreciate this opportunity. So let me start by give an overview of the type of research that I'm doing. But let me start by just talk a little bit about myself. So I got my undergraduate degrees from Tsinghua University, and then I was extremely fortunate to go to the Stanford and actually get a fellowship that will support most of my PhD years that essentially allow me to take whatever courses I want to take. So I take a huge number of courses, got a bunch of degrees at Stanford. And then, yeah, so my advisor told me you have to graduate. So I graduate and go to UC Berkeley to do a postdoc. Still stay in the Bay Area. There, the first year of the postdoc is interesting because there's a joint appointment between UC Berkeley and the Lawrence Berkeley National Lab. So I get a feeling about working for National Lab, how that should look like. And they actually have very strong energy groups like building energy modeling and so on and so forth. I was able to build some connection there. So the second year of my postdoc is all in Berkeley because I'm a little bit tired of just going back and forth between up here, which is the Berkeley lab, and UC Berkeley. Anyway, so I joined Purdue ECE in January this year. I'm still trying to get used to the weather. After I come to the Purdue, this is really the first time I realized why people could be so concerned about the fact that the winter is coming. The winter is it's brutal for me anyway. And I'm still looking for someone to play ping pong with. Yeah, so I like to play ping pong as a hobby, but I'm still trying to figure out where I can play and who I can play with. All right, so that's about myself. And then in terms of research, all my PhD research have been focused on energy and in particular electric power energy systems. So starting from my postdoc, I started to branch out a little bit by looking into transportation system as well, and in particular, look at the nexus between energy and transportation system. So let me just give you an extremely high-level overview of some of the challenges that we're trying to address in power systems. So I said this is a grand challenge. Of course, there are many of such grand challenges, but this is one of the most important ones. Okay, so the basic idea is that in the past we have, for power system, we want to make sure supply equal demand at any instant of the time because of the physics of the power flow. And in the past we have controllable supply, and we are basically controlling the supply to meet demand. And by controllable supply, we mean, coal power plants, gas power plants. That's essentially power plants. You can determine its set point, determine how much power it will produce in each of the hours. Nowadays, we're in the process of integrating some amount of renewable. It's still not a lot. And how renewable uncertainty is coped with nowadays, it's really just using standby generation, which are called reserves. They are still fossil fuel based generations, and they produce greenhouse gas, and some of them are dirty, so we don't really like that, and they are very costly as well. But we are really working to a future where we are going to have more than 18% of the power generated from renewable or even more. Right, so this simple equation now becomes that maybe you are still going to have a small amount of controllable supply, and then plus the uncontrollable renewable, because renewable power supply is really determined by the weather condition, and then the total have to be matched with the demand, which to a large extent is uncontrollable, right? Because we work in a room, we for example, turn on the lights, turn on our computer, we don't really think about how much power we're going to consume. So if we keep consumer behavior like that, then the demand will be uncontrollable. And then by the end of the day, a lot of things have to be changed to make sure the power balance equation can still be held at any instant in time. Okay, so for listening to hold, we really need transformation both at the supply side. We need to think about how do we better manage the remaining uncontrollable supplies. And we will need to have innovation over the power network, because power network are extremely complex, and you actually have a lot of physical constraints dedicating, how much power you can flow on each line of the power network. And if you violate any of these constraints, you're going to have a blackout, maybe for a region or even for the entire grid. Right, so over the power network, potentially we need to think about better controls or maybe introduce more resources like energy storage. And then on the demand side, we also want to think about, can we introduce some level of controllability on the demand side? Maybe for some of the existing load, maybe some of the homes, they are going to install smart home systems. Potentially we can leverage that to help us, tune some of the flexible demand to some extent. And then we also have a lot of new demand that is coming online. For example, we are in the process of integrating a huge amount of electric vehicles into our system. So we want to think about what is the best way for us to manage all this EV charging load. Or maybe these electric vehicles, they have all these batteries. Potentially we can have them to provide some type of grid service. So potentially they can be connected to the network, or maybe, sometimes you can discharge some of the EV batteries in some special occasions. Okay, so in my past research, I actually have touched upon each of these three different elements, but today we are going to actually focusing on the demand side. And I'm actually going to tell you a very specific project that's sort of at the nexus of energy and transportation system. And the idea here is that potentially, if we are going to have more and more electric vehicles, then potentially we can use some of the EVs. Maybe they are for higher electric vehicles, but potentially we can use some of them to provide certain type of energy service to the grid. Okay, so what I'm going to show here is really they are indeed this kind of energy service this EV can provide, and they can be extremely profitable. So indeed, we actually have incentive to do something like this. And here's the use case that we are going to consider, or the energy service we are going to consider, is called demand charge reduction. Now, for people who are not familiar with demand charge is something that commercial and industrial electricity users, so all these large electricity users, think about a factory or maybe a grocery store, a business building, they will need to pay every month. So for this type of users, their monthly electricity bill will consist of an energy charge component that scales with the total number of kilowatts that this user is going to consume, and a demand charge component, which scales with the maximum energy consumption over the month. Right? So demand charge is calculated by you take the demand rate, multiply with demand, and demand here is defined as you take the maximum 15-minute energy consumption divided by the 15 minutes. So here 15 minutes is referred to as metering interval. That's because of time resolution utility company, they can measure your energy consumption and collect your energy consumption data. Usually this is 15 minutes for United States. Some of the area we actually have 30 minutes. Okay. So just as an example, this is the energy consumption time series for one of the particular users over a month. So here on the right, to calculate energy charge, you basically first calculate the total energy consumption. You sum up all the energy consumption, all the points in this curve, you will be able to get this number. And to calculate demand, you basically take the maximum and divide by 15 minutes. So it turns out that because this is hourly data, so you will actually get this number. And then we are going to multiply the energy consumption and demand with the energy rate and demand rate. And as you can see, the demand rate is dramatically higher than the energy charge, energy rate. And this data is got from one of the utility company in California, and this is for small and medium business. And for large business, the demand charge rate can be more expensive. So for this particular user, it turns out that the demand charge is about 15% of the energy charge. And it had been reported that demand charge can be even higher. It can account for 15% of the muted. Okay. So so actually C&I electricity user, they have strong incentive to reduce their demand charge. And then one interesting aspect about demand charge is that only peaks matter in this calculation. For example, for this particular user, if he can manage to reduce the energy consumption for the peak metering interval just by 4.1 kilowatt hour, we can dramatically reduce the demand charge by more than $300. Now, if you want to further reduce demand charge, you will have to further shave the second peak and third peak and so on. And in general, the reduction potential for demand charge will depend on the statistics of the peak. Okay, so there are different ways to potentially reduce demand charge. For example, you can ask the user to curtail their energy consumption, but we're talking about commercial and industrial electricity users. So a lot of time, the peak actually happened during business hours, so it's very hard to curtail. Another possibility is that this user can install dedicated energy storage. But if you just focus on demand charge reduction, maybe you just have to reduce energy consumption, for a couple of times over a month. And if you install a stationary battery just for that, the utilization is going to be extremely low. And our idea here is that potentially we can share a small number of mobile energy storage units and move around different users, if different users are going to have their peak at different time. Okay, so this idea of mobile storage in practice, you have different implementation. For example, you have this truck-mounted mobile storage unit, and you have this sort of small mobile storage unit. You can first charge it up and move it around to charge another electric vehicle. And here, our focus here will be use an electric vehicle together with a bidirectional EV charger as mobile energy storage. So basically, we're trying to use a battery inside of EV as mobile storage for this. And what we are proposing to do is we can potentially implement some sharing economy business model like what Uber and Lyft have today. And the idea is that the supply side of this business is going to have EV drivers who are willing to provide the service, and demand side going to have commercial and industrial electricity users. Think about, for example, you have a grocery store, and here we assume the user also have a bidirectional EV charger that's installed in place. And in between them, we are going to have a matching platform, just like what Uber and Lyft have today. So how this business model work, where the user, if he anticipate that potentially he's going to have his peak demand in some of the metering interval, the user can request through user's app to have an EV to come to his location, and the matching platform will find a nearby EV. The EV driver will go to user's location, connect the EV to the bidirectional EV charger, and discharge its EV battery when it is needed. Okay, so this is an example of sharing economy, and this business model only makes sense if two conditions are met. The first condition is that peak of different users tend to happen at different time. While this is necessary, well, if you have 100 users and all of them going to have their monthly peak exactly at the same time, then you are going to need 100 EV to serve them, right? So there's no case for sharing whatsoever. But if all these 100 users are going to have peak at different times, then potentially you can just share a very small number of EVs to serve a large number of users. All right, so this is one of the very important conditions. And the second condition is that for any business model, the benefit or the revenue need to be able to cover the cost. So what I'm going to show next is that both of these conditions will be met. So first is a temporal statistic for the peaks. What we did is that we took an Irish data set, which contained 100 commercial and industrial electricity users over the course of 17 months. So here, what's shown here is a temporal distribution of the peaks. So the x-axis is the index for the metering intervals, and the y-axis is the number of users who are going to experience their monthly peak in that metering interval. So as you can see from the maximum number on the y-axis, here the maximum number is 2. So basically it says that the maximum number of coincident peaks over this 100 users is 2, right? So if you ignore the time that's needed for you to move EV around, for you to recharge EV battery, this result says that 2 EVs is sufficient for you to serve 100 users. Now you may say this is something special, we actually did the same analysis for all the 17 months. It turns out the same observation hold. We did the same analysis for another data set, the same observation hold. So basically, the peaks of different users tend to happen at different times. So this is a very strong case for sharing economy. Okay, so for the second condition, what we need to track, first of all, the major cost item we need to handle is really the cost of this bidirectional EV charger, because nowadays people don't have that. And given the interest of time, let me just talk about the conclusion. The conclusion here is that we can just use an AC level 2 bidirectional EV charger. We don't really need a fast DC charger, so potentially the cost is low. And here we actually show that even if each user just make 1 or 2 requests per month, the revenue from this business or the cost reduction that come from the demand charge reduction going to be able to cover the capital and installation costs for this AC level 2 bidirectional EV charger. Okay, and then there are other additional cost items, but here the major result that we got is that after you have account for the capital and installation cost, the revenue will still be able to provide each EV driver at least $15 per each service session. And this is compared with driving for Uber. So for our service, you only need to request EV drivers to park at a user's location, maybe for 15 minutes or maybe for 30 minutes. But if you drive for Uber for one entire hour, the hourly salary is around the same level. So this is basically saying that potentially this can be attractive to EV drivers as well. Okay, so there are a number of current and ongoing efforts related to this business model. We are trying to address uncertainty in this analysis, trying to test technical feasibility, and we are also in preliminary discussion with Uber, trying to understand the potential of commercialization. There's something else that we are trying to look into by basically thinking about, can we use a platform like what Uber and Lyft have today to use their electric vehicles to not only provide transportation service like what they are doing today, but also provide electric service. Because of the interest for time, I'm not going to be able to have time to talk about this, but basically we formulate this as a profit maximization problem under various type of equilibrium constraint, trying to look into the incentive capability constraints for the EV drivers, as well as the traffic flow in a traffic network. So this will end up to be a non-convex optimization. We're able to find a tight convex realization of that. So that's essentially allow us to solve for this problem, even if we have a very large network. And we are able to also get some closed form result under some special conditions for the system demand, where we also derive some insights about how these two different types of service, they can complement with each other. Okay, so we did some analysis with real data from San Francisco. This demonstrates that not only this adding electric service to a transportation service help this transportation network company improve their profit, it potentially can also help you to reduce the congestion caused by these transportation network companies, because you can route some of the empty EVs to the parking lot of the commercial industrial electricity users and have them to provide electricity service. And otherwise, they may have to just to drive around and look for customers on the street. All right, so as a summary of the research part of this talk, so what I'm essentially trying to tell is a story here where we are trying to use data-driven insight, where we're looking into the data and trying to identify this interesting observation that different users tend to have their peak at different time. And based on that, we're trying to define new research problems and potentially trying to look into new opportunities that potentially help us incentivize the demand side of the electricity system and potentially have the EVs to provide various type of service to the energy grid. Okay, so that's everything I want to talk about today. I'm happy to answer any questions. Thank you so much.
Thank you very much, Junjie. And we will see also several questions at the end of the panel. And actually, Professor Deng Sun already types a response to you about the ping pong. So for all the attendants, please feel free to type all your questions in the chat window while during the presentation. So next we will welcome Ahmed, who is a assistant professor from Purdue Computer Science, and he received his PhD from UC San Diego. And his research interests include machine learning, computer vision, AI, and also develop intelligent robotic system. So Ahmed, it's all yours.
Thank you for having me here. Can everybody hear me?
Yes.
Okay, I hope. So here I joined Department of Computer Science, where I direct Cognitive Robot Autonomy and Learning Lab. And in this, I will briefly discuss about my research background in just one slide, because I want to focus more on my future research interests and what my lab does. So let's get started. So I started my research quite early during my bachelor. During that time, I focused on planning and control, where I proposed a variety of new algorithms to speed up these methods for multi-agent systems, such as here, as well as for dynamic environment. This is the example of dynamic environment in which Blue Robot need to get to the goal while avoiding all the collisions in an unknown environment. And we also use similar techniques for RoboCup competition, where we had like 2 teams of humanoid robots, each with 6 robots, and they had to play the robot soccer with each other. And it required a variety of decisions such as like defending, kicking, walking, all these in like respecting the stability of the system. And we also deployed this on a wheelchair, which was done in collaboration with Sakura Wheelchair Association Japan. I basically led the team of integrated perception and planning for this wheelchair, and we gave some nice demos like how it can work in dynamic environment. Then I moved to Japan for my MS. There I worked with a variety of robots, but this is the main one that I want to highlight, that we built a system which was able to interact with people in completely uncontrolled environments. So there was no supervision or anything. For 14 days, we left this robot in public and let it interact and learn. So it was like really exciting, and I learned like a lot of things, how difficult things can be in practice than in simulation. So it was really a good learning experience. Then I moved to US, where I combined my experience on like planning and control, human robot interaction, and bridged it with machine learning. There I mainly focused on manipulation planning for different tasks, such as for assistive robots as well as for robot surgery. And that's all about my background. Here in Purdue, I direct Coral Lab, and we are interested in solving common daily life problems, because for robots, things that are very easy for human can be very difficult for the robot. And things which are difficult for human might be very easy for the robot to solve. For example, the game of Go, which is like Asian version of chess, and it has like a lot more moves than the traditional chess game. And this game, like recently, a AI system was able to beat best player. And these kind of problems, which are like limited in the sense that the noise, there is no noise from the real environment, and there is no like dynamics or physics involved. So this problem makes things a lot easier. Whereas when we go to real common daily life problems, the robot fails most of the time. For example, here you see in this video, this is from DARPA challenge, just rotating this one valve is very difficult for the robot. And I can list a variety of problems where current robot system can fail, such as pouring water, opening door, like all those kind of scenario where a bot need to interact with the environment becomes very difficult for current algorithms. So in my lab, we are interested in solving those kind of problems so that we can build systems that can assist people in their daily life, as well as in hospitals or in the manufacturing as well. And in my lab, we often revisit this pipeline of like robot should perceive the environment, then it should plan what it wants to do, and then act accordingly. For instance, in navigation, this could be like creating the map of the environment. And once you have the map, let's say you want to go from one point to another, you need a plan. How would you move from one point to another while respecting all the constraints? For example, collision avoidance, robot stability, speed, like if I want my robot to go as fast as possible and reach the target with some velocity. So all those kind of constraints needs to be respected in the plan. And then robot acts in the environment. And during action, because there is actuators can be noisy, sensors can be noisy, how it can replan real time so that it can fix all those errors while still sticking to the original plan given by the planner. So in my lab, we revisit the stack again and again to solve a variety of problems. And we not just focus on car navigation, we use this stack to solve planning and control stack for a variety of systems, such as for multi-legged robots, for drones, so that they can move as fast as possible in cluttered environment. And we also use these techniques to plan the motion of like artificial agents, such as for video games and for animation industry, such as Disney. And not just static environment, my lab also focus on the dynamic environment, where robots need to move in cluttered environment while avoiding clean and getting to the target as quickly as possible. So this was like one of the research interests, which is like autonomous navigation and control. We are also interested in solving manipulation planning problems where robot actively perceive the environment and based on some task, it decide what to do and manipulate different objects in the environment. And we assume different kind of constraints such as stability constraint, or for example, in cutting tasks, robot need to orient knife in certain way so that it can perform the task. And here's the third example of plowing. Now robot, both hands are tied with this tool and they significantly restrict the robot motion. So we are interested in solving these kind of complex manipulation problems based on just sensory data. So we don't want to assume that we know everything in the environment. We want to assume we just have the visual information. It could be depth information, or it could be just RGB information, and how we can use that to solve these problems. And not just for assistive manipulation, we are also interested in like manipulation that appears in surgical tasks. For example, in this fraction of second, robot had to perform variety of tasks from capturing this needle, inserting it into the grape, and then tying the knot. Within this fraction of second, robot had to do variety of tasks, and we are interested in coming up with fast methods so that we can do that real time instead of making someone wait for hours, so that robot can make the decision and act in the environment. And lastly, my lab also focus on mobile manipulation with multi-agent systems. So for example, for the rearrangement of different objects into different other orientation. And we are also interested in how we can allocate resources to different robots so that they do not conflict with each other and optimally achieve the given task. And the third that we are interested in my lab is human-robot collaboration. So this is the like long-term picture, like what I would like to see when I retire is like robot capable of like helping people in dynamic environment. Here you can see one robot is interacting with the person to guide them, other robot is carrying the cart. And if you just imagine that one problem of like lifting a cart or like maneuvering it, it's an extremely challenging problem. You need to respect the cart dynamics, their physics, and sometimes often in the shopping mall, the cart are in really bad situation, like their wheels are worn out, and how we can solve those problems in realistic scenario, and how we can capture the system's limitation based on limited interaction real time. So these are the three projects that we focus on in our lab. And this is the like overall like summarized roadmap, like where my lab will be progressing in the future. So now with the advancement, we have multiple sensors. We have vision sensor, we have biomimetic sensor that can give me like biological information of the people. We have like sound sensors, we have tactile sensor, we have other like text kind of information available. How can I learn a multimodal space so that I can predict one modality from the other modalities? And we humans do that in our daily life. Imagine you are in a dark room and you have to search for a torch or keys. Just based on your experience, now your visual information is cut. And now just based on your experience, the person will navigate the environment, get to the drawer, and just by touching different objects and hearing their sound and what kind of sound they produce, we will be able to recognize that object. If we by chance touch the keys, they will make certain sort of sound. And just by their sound, I can recognize, okay, these are the keys. So I'm interested in multimodal perception so that given certain modalities, I should be able to infer missing modalities. And once I have that multimodal representation, how I can use it for state estimation to predict human behaviors, to predict their biological state, as well as the robot state itself and the environment state in general. And once I have this robust multimodal state estimation, how can I use it for solving cooperative planning and control problems, to develop contextual reinforcement learning algorithms that make use of these multimodal spaces, and then applying them for dexterous manipulation as well as multi-agent system to solve daily life assistive robotic tasks as well as autonomous driving and autonomous surgical tasks. So this is the entire roadmap, like where we will be heading in the future. And we basically drive our ideas from a variety of fields such as artificial intelligence, machine learning, computer vision, optimal control, optimization, computer graphics, neuroscience, and psychology. And these are all the fields that I have worked in order to design my robot cognition algorithm so that they can control robot body in an intelligent way. And to help people gather up this diverse knowledge, there's also an upcoming course next semester in CS, it's CS 593. There we will go through this entire pipeline of perception, planning, and control. And these are some of the topics that I will be covering for multimodal perception using deep learning, then AI and learning-based planning algorithm that include search-based method, optimization-based techniques, under advanced constraints such as velocity constraint if I want my robot to get to certain location as fast as possible, or I want it to respect some stability constraint. For example, if I have a mobile manipulator and it is carrying a glass filled with water, it needs to respect that it shouldn't tilt that glass at all and make sure the liquid stays within it during the motion. And the third part will be how we can execute the plan as accurate as possible. There, I will go through a variety of control techniques as well as deep reinforcement learning for robotics. And there will be like, and how we can solve this entire perception, planning, and control stack in an end-to-end manner. And students will hopefully explore that through different projects. So that would be all. Thank you very much. And if you have any questions, feel free to email me. And that's it. Thank you.
Thank you, Ahmed. Thank you very much. And I said, please, feel free to type your question in the chat window. And we need to move to next. Next will be Yu She, who is an assistant professor at Purdue IE. So you received his PhD degree from Ohio State and also worked on a postdoc at MIT before joining Purdue. So his research basically include intersectional mechanical design and also sensor perception, dynamic control, and also human-safe collaborative robots, and also software robots. So you have received several types of awards, especially Best Paper Award, like from the Journal of Mechanism and Robotics, and also from RSS and the DSCC. So you, all yours. You're muted.
Yeah. Can you hear me, Xiaoshuai?
Yes, I can hear you now.
Thank you. Thank you for the great introduction. Yeah, actually, for the award, most of them kind of finalists. Only one of them is Best Paper Award. Yeah, so today is a great pleasure to be here to share with you my research. And first, I would like thank Xiaoshuai and Shreya's organizing this great platform and have this great opportunity here. Today, I will talk about towards safe and high-performing collaborative robots, kind of synergistic to Ahmed's research. He kind of more on the high level planning control. I will focus more on the local control, local perception, tactile sensing, and more mechanical side. I'm an assistant professor from industrial engineering. I just joined here in August 16. I will start with a little bit of introduction about myself. I grew up from a beautiful village from Changsha, Hunan in China. And then I went to Taiyuan University of Technology for my bachelor degree in mechanical engineering. I studied a lot of mechanical design, and also I get interested in autonomous system, DOVs like microcontrollers, Arduinos for electronic components. And then I moved to Harbin Institute of Technology, Shenzhen in China for for my first master degree in mechanical engineering, and I study robotics, kinematics, dynamics, and control with like 7 degrees of freedom redundant robot. And then I obtained my second master degree in electrical engineering at Ohio State University, and also a PhD degree in mechanical engineering. And at Ohio State, I focus more on the mechanical design and modeling and manufacturing of soft robots, compliant robots, compliant mechanisms. And then I moved to MIT from a postdoc at the Computer Science and Artificial Intelligence Lab. And at MIT, I focus more on the tactile perception, robotic manipulation. And my research is at in the section of mechanical design, sensory perception, and dynamic control. I will start with a brief introduction about the big picture in the field. And we knew traditional industrial robots, they are fast and precise. They have very high performance. However, the safety, they are not very safe because they may hit or have collisions with human, may cause severe outcome. So most of the time they are put in the cage to physically isolated from human to ensure safety. And soft robots, on the other hand, they guarantee safety because they will deform upon impact, and they guarantee safety, but sometimes the performance is limited. The payload, position control are challenges for soft robots. And existing collaborative robots, they're kind of in between. They provide kind of a great performance. Still, they have some limitations. For example, UMI, as Ahmed showed in his presentation, actually the payload for UMI is 0.5 kilogram, which may be too small for many manipulation tasks. So my research goal is to develop inherently safe and high-performing robots that can share workspace with human and perform daily manipulation tasks. And today I was going to discuss four research projects in this domain: variable stiffness robotic arms, soft robotics, tactile sensing, and robotic manipulation. And I will give a very high-level brief overview for these four projects. So for the variable stiffness arm, I studied the design, manufacturing, and modeling of the robotic arms. They will have very large deformation, so the kinematics and dynamics will be more complex than the traditional robots. And I also studied the optimal stiffness control. Here's one example one project I involved, and this is the variable stiffness robotic arm. It has a vacuum bag covered on top of the like 3D printed material and the flexible membership here. And by control the air pressure in the vacuum bag, we can control the stiffness of this manipulator. So it changes the stiffness around 80 times. And in the stiff mode, we can use for, say, high payload application or position control. In the soft mode, we can use for like safe interactions with human. So here's another design of the variable stiffness arm. The goal is the same. We want to develop a variable stiffness arms, change the stiffness, actively tune the stiffness. This is another method. It's by shape morphing. For example, this arm has two flexible beams on the side. Here is a cross section of this arm. By control the shape of this flexible beam, we can change the second moment of inertia of this robotic arm such that we can get a variable stiffness. And here's another design of the variable stiffness link using cable-driven system. So the second direction is hybrid rigid soft robots, because I mentioned soft robots itself kind of have limited performance from a lot of situations. And of course, soft robots, so for some application, they do not need high like payload or position control. That would be perfect. But for some situation, we need the soft robots has some capability to grasp some payload. So in this case, I think hybrid rigid soft robots will be one option. So I studied smart material actuation, modeling, and the shape control. I use embedded vision sensor and machine learning to study the proprioception, tactile sensing, and object classification. And here's one example for these hybrid rigid soft robots. It's an exoskeleton covered soft robotic gripper. And here the yellow parts are the soft finger body made by silicon rubber, and it is covered by the exoskeletons. So the exoskeletons are rigid, provide powerful grasping force, and the soft part provides safe interactions with the objects. So the contribution for this work actually is not from the mechanical side, it's from this perception. We use embedded camera here for the perception for these soft robots. This is the camera view. Because soft robots, they have very complex deformation, very difficult using traditional mechanical sensors to precisely estimate the proprioception or the shape of the soft finger. Here we use embedded camera because camera provide high resolution image data, and then we can use machine learning algorithms to estimate the shape of the soft robots. Here we can see the tactile information, and simultaneously the camera will track the motion of the markers on the side to estimate the shape of the soft finger. Here is a result for the proprioception, means the shape of the finger. On the left, we see the actual finger pose, the finger shape. On the right, we can see the estimated shape of the finger. We get a 99% accuracy within 1 degree error using our algorithm. And here's another task for object classification. So with the tactile information and the proprioception information, we train another neural network to identify the objects, including the size of the objects and the shape of the objects. And here's another project of the hybrid rigid soft robotic gripper. We have the smart material actuator as a skeleton embedded inside of the finger. So it's a shape memory alloy, and is covered by the soft silicon rubber as a safe interface for with the objects or with human. And I studied this very nonlinear hysteresis modeling for these smart material actuators, and it provides a very high ratio of the power over the weight because due to the material property of the smart materials. And the third direction I want to discuss is tactile sensing, because eventually we want to have these robots perform manipulation tasks. Then the tactile perception is critical for manipulation. And I use embedded vision tactile sensing for manipulation. So with this tactile sensor, we can estimate the object geometry, object pose, and the object material property, normal force, shear force, and we use a theoretical model and deep learning for 3D reconstruction. And here's the application for this tactile sensor. For example, we have this robot here, we have the gripper, and we have the tactile sensor. So the gripper is going to grasp a plate in the kitchen. And this is the contact between the sensor and the objects. This is the camera view of the sensor. So we have embedded camera here. So it's called a GLSI, embedded vision sensors. And on the right, we can see we can scale down this tactile sensor as a finger shape, finger size. We get like geometry information and also 3D reconstruction of the objects. I will talk more about this sensor in the next slides. So here, I showcase how the sensor works. This is the sensor. We have embedded camera here, and we have a soft gel on the surface, and also we get some patterns on the surface. This is the camera view from this sensor. When we press the screws on the surface, we can see the geometry information of the objects. And our algorithm will track the motion of the markers. So these yellow arrows approximate the shear force applied on the surface. And more importantly, we can also get the 3D reconstruction, the depth image from this tactile sensor. So the 3D reconstruction has two major functions. First, it's kind of normal displacement. So we can use finite element method to estimate the normal force based on this 3D reconstruction image. The second major application for this 3D reconstruction is for pose estimation of the objects in the gripper, and I will show more details in a little bit later. And here we show more testing result. The objects pressed on the object pressed on the sensor, the sensor data, and the depth image. And here is one example of the pose tracking. So the left, we see the actual pose of a sphere, and on the right, we see the sensor data. So in the middle is estimated pose from algorithm. And we can also track the pose of a cube. So the left one showing the actual pose of the cube. The right one, we see the sensor data, which is here. And in the middle, we can see the estimated pose of the objects. So using this data, the pose estimation, we can design controllers for robotic manipulation, which come to my fourth topic. Yeah, so the first topic is robotic manipulation using those tactile data. And here we are specifically, I will talk about robotic cable manipulation. I will talk about cable grip control, cable pose control, data-driven method for cable sliding dynamics, vision-based tactile sensing. And so now we want to use this gripper to manipulate a cable, which is flexible objects or deformable objects manipulation. And here, as I mentioned, we can get the pose estimation. We first use photometric stereo, get the depth image, and we threshold in the depth image. Then we can have the contact region as we show the white ellipse in this in the middle video. And then we use PCA algorithm to find the principal direction of the cable, which is the red line inside of the white ellipse. So on the right is the yellow arrows approximate the shear force applied on the cable. Then with this tactile feedback, we design controllers for robotic manipulation. So here is an example we demonstrate. The gripper can follow up an earbud cable and find the plug inserted to the cell phone using purely tactile data. Here, we have two controllers. The first controller is to make sure the gripping force is just right. The gripping force cannot be too large and cannot be too small. If the gripping force is too large, then we have too much friction when we sliding along the cable. And the gripping force cannot be too small. Otherwise, we do not have good tactile signal. The second controller is to make sure the cable was remained inside of the gripper when it's sliding along the cable. So we use LQR controller for this robot, which is UR5, to make sure it's moving back and forth to keep the cable remain in the gripper when the gripper sliding along the cable. So yeah, my future work will focus on the inherently safe and high-performing robots that can safely work in human shared environment, like the robot assistant, robot waiter, and the home robots, and they can efficiently perform daily manipulation tasks. That's end of my talk, and thank you. I would be happy to take any questions and discuss further details with you. Yeah.
Great. Thank you very much, Yu, and very nice demos. So we will leave your question also at the end. So next we'll go to Abolfazl, who is an assistant professor at Purdue AAE, and he also received his PhD and postdoc from UT Austin. And his research interest includes networks and collaborative learning systems, especially with limited resources and data. So Abolfazl, it's all yours. You might mute yourself. While we're waiting.
Hi, can you hear me?
Yes.
Okay, yeah. So sorry, I'm trying to share my screen. So can you see my screen?
Yes.
So So since I have this two monitors set up, do you see the presenter view or the correct one?
Hey, current one, pretty good. We can also hear you. Yeah.
Okay, okay.
Please go ahead.
All right. So yeah. Thank you. Thank you for the introduction. So today I'm just gonna talk briefly about the work that I've been doing in the past few years, and what's my vision and what I'm gonna do in the times that I'm gonna be in Purdue and establishing my lab. So just a brief overview and a few words about who am I. So this is me, and this is essentially a picture of me. I think that I took the first day of classes. So it's the first selfie from my office. So I just want to show you to see whether you can identify any changes and whether I was successful in surviving the first months of being an assistant professor here. But anyway, yeah, so my name is Abolfazl and I'm originally from Tehran, Iran. I was born in 1981. And I got my bachelor's degree in electrical engineering from Sharif University of Technology. So there, I wasn't sure what I want to do for research, and I was fortunate enough to do an internship in Hong Kong University. And there I was, I got familiar with optimization, machine learning, data science, and I got motivated to pursue research and get a PhD. Therefore, I applied to the US and I came to the UT Austin. I got my master's degree and PhD degree, and I also was at UT Austin for a year and did my postdoc there, where I focused on the collaborative learning systems, and I worked on designing algorithms with probability guarantees using techniques from signal processing, machine learning, and optimization. And now I'm here at Purdue, the Elmore Family School of ECE, and I just started this semester. All right, so today I'm just gonna talk about the work that I've been doing. So I'm gonna start with a little bit of motivations. So my work is related to collaborative learning systems. So connected systems are everywhere. They have lots of applications in emerging scenarios such as satellite mesh networks and smart grids. And so it's important to ensure that we can come up with information management algorithms and techniques to ensure a reliable and effective deployment of in these systems in our life. So there are certain challenges with collaborative learning systems that I'm just going to briefly talk about. And in the past few years, we have been focusing on addressing these challenges. So first of all, the collaborative learning systems are growing. And for instance, currently it's estimated, and we have data that shows that there are currently more than 30 billion connected systems, connected IoT devices. And it's estimated that by 2025, more than 150,000 devices are going to be activated per minute. And these devices have different characteristics, right? So each one has different hardware, they are being used by different people. So there is a high degree of heterogeneity. And when we talk about these devices communicating, it happens that many of these devices are operating in environments that have unreliable communications, and their communication capabilities might not be great all the time. So they are also characterized by having limited and unlimited bandwidth. So in order to ensure that collaborative learning systems can perform effectively, it's important to come up with scalable methods that are able to deal with heterogeneity of these systems. So, yeah, so another challenge that is related to collaborative systems is that these systems are typically consist of embodied agents. For instance, if you consider a network of satellites that are operating in a low Earth orbit, for instance, performing some sort of navigation, or in a network such as SpaceX to provide internet for everybody. So these agents have different sensors. They are moving in rapidly evolving environments. And because they, for instance, in the case of satellite agents, because they are operating in high frequencies, it turns out that they need to consume a lot of energy. So therefore, the cost of gathering observation, the observation gathering for these agents is going to be quite costly. So and a challenge and a direction that we have been working on is that how can we design low cost and energy efficient methods for collaborative learning systems that are operating in rapidly evolving environments. So yeah, so today I'm gonna discuss 3 directions that I've been working on in the past few years. And the first direction that I'm gonna talk about is related to coming up with communication efficient federated and distributed learning for network systems. So specifically what we have been doing is that we have focused on problems of training predictive models in a collaborative fashion. And then in this scenario, we have agents that each one has access to a local collection of data, and we need to ensure to be able to effectively use all of these data sets and coming up with communication strategies in scenarios where the agents have access to limited communication budgets. And what we have been doing, we have designed methodologies in order to ensure that the learning algorithm can converge to a near optimal solution with provable guarantees and can effectively learn a model to perform our inference task. So just a little bit motivation, an example of learning a predictive model is in the case of autonomous cars and connected cars, right? So there we have an autonomous car that moves in an environment and gathers some a collection of data, and its goal, for instance, is to use this data to perform perception, to perform to be able to identify critical objects such as pedestrians or traffic signs, and based on that makes a decision, right? But what will happen is that in many scenarios, the data that the agent gathers is not enough by itself. So the agent has access to limited local data, and what it does is that it collaborates with other agents, with other connected cars via cloud. Okay, so these cars, you can imagine that they are connected with each other using a cloud, and each one has access to a local collection of data. And by collaboration, they can potentially improve the efficacy of the inference algorithm as opposed to relying on their own data. But as I talked about, each agent might be in different environmental conditions, right? So it might have access to, in some situation, it might be in a situation that it's not able to communicate messages to the cloud. So the communication is expensive, and also each vehicle by itself is different, and there is a high degree of heterogeneity that we as a designer need to be able to deal with these challenges. So in order to tackle this problem, we identified that there are 3 main components that we need to address for a collaborative learning problem such as federated learning. First, we need to ensure that the local optimization subroutine that each agent uses is accurate enough and is able to deal with the fact that the gathered data from the environment is noisy. So what we have been able to do is to come up with novel and recursive estimators, if you will, in order to reduce the amount of noise in the data. So you can imagine that this is the baseline, essentially the information that you get from the by using a simple, let's say, optimization subroutine. But we've been able to show that if you incorporate a recursive type of estimator, as the learning algorithm converges to finding a solution, then this estimator is able to reduce the amount of noise and reduce the amount of variance in the data. So by incorporating this estimator, we are able to come up with an effective local optimization subroutines for the agents. The second component that we need to design is essentially what's an effective way of aggregating all of these messages that the agents communicate to the cloud. So we were able to sort of start our work from just a very basic way of averaging, right? The first thing that comes to mind is to just take an average of all of the messages that you receive. So what we have been able to show is that you can imagine that this simple way of aggregating, essentially averaging, can be thought of as being a generalized notion of a gradient. So essentially some sort of first order update. So because this original baseline method, when we were talking about the local optimization subroutine, had a problem with noise and variance in the data, the simple way of aggregation also has a problem with the noise that now stems from heterogeneity. Not because of the noise in the data, but because of the fact that these agents are heterogeneous. So we have been able to sort of use this idea and design a new aggregation method for the server in order to aggregate all of these messages that are communicated from our agents to the cloud. And we refer to these two subroutines, local momentum-based variance reduction and global momentum-based variance reduction, right? Local because it's used locally by the agents, global because it's used by the server in order to aggregate messages. And finally, we need to ensure that we can deal with the fact that the communication might be expensive, right? So remember, in many of these scenarios, we are learning a predictive model, right? Like a deep learning model. Okay, so and there are millions of parameters that we need to learn, and essentially we need to communicate millions of parameters every communication rounds from these local agents to the server. So this is quite costly, and communicating full precision messages it's not possible in practice. So what we have been able to do is to rely on quantization schemes and severely compress the messages that the full precision messages, and we have been able to show that our algorithm is able to achieve an optimal rate of convergence, even though you are using compressed messages like quantization in order to significantly reduce the amount of communicated bits in your algorithm. So we have been testing this in a few problems. I'm just showing an example here of collaborative learning of deep learning classifiers. So essentially, we have a bunch of images like the CFAR10 dataset, which is a standard dataset in machine learning. And our goal is to learn a deep learning classifier that has, let's say, 2 hidden layers. And we consider 2 settings, a homogeneous setting and a heterogeneous setting, right? The homogeneous setting is the case that the data that each agent has is roughly the same as the other ones, right? So essentially, you can imagine that there is no need for collaboration, because if each agent relies on its own data is essentially quite similar to the data of the other agents in the network, right? And in this scenario, what we have been able to show is that the baseline is able to perform well, but our algorithm performs better. Why? Because although there is homogeneity and the data between different agents is the same, there is still noise in the data. So this figure shows that our local optimization subroutine is able to effectively reduce the noise and variance in the data to ensure that the training loss as well as the test error are significantly improved compared to the baseline. But if you consider the more interesting scenario of heterogeneous networks, where the data between different agents is significantly different, then we see from this figure that the baseline method has a problem, right? The convergence curves go crazy, and there is a large noise in both the curves for the training loss as well as the test error. But due to the fact that we have been able to use global momentum-based variance reduction at the server in order to deal with heterogeneity, our proposed algorithm is able to have a smooth convergence to a solution. So not only we have a faster training, but also we have a better generalization. And overall, we've been able to show that our algorithm is able to have almost an order of magnitude savings in terms of the communicated resources compared to the baseline. So a second line of work that I've been working on is related to performing observation, selection, and information gathering for resource-constrained networks, such as sensor networks. For these networks, we have agents gathering observations, but because they have limited resources, they are not able to, let's say, communicate all of these observations to a center where the fusion happens. So their goal is to identify a best representative subset of the observations and communicate that subset to the server, to the center, in order to perform fusion and, for instance, tracking. So in this work, we are motivated by target tracking applications. For instance, let's say we have a collection of UAVs gathering noisy and time-varying observations from some unknown state, for instance, the location of some unknown objects moving in an environment. And as I mentioned, our goal is to perform observation selection because of the fact that we have limited power in order to ensure that the estimation error is as low as possible. So there are two questions that we identify here. The first question is, what's the best selection criteria in order to select these observations? And secondly, what's the best way and efficient way of performing these selections in order to ensure that we have also some sort of performance guarantee? So in order to do so, we have been focused, since our goal is to reduce the low mean square error, we are focused.
So would you mind to more quickly wrap up, because we already almost reached 5 o'clock.
Okay, sure. Okay, yeah. So just a quick remark here about this is that we focus on the error covariance metrics, and we were able to design objective functions, if you will, to perform observation, selection, and information gathering. And we have been able to show that these objective functions that we define have nice properties. For instance, they are monotone and weakly submodular, which enables them to be optimized efficiently, for instance, using a greedy algorithm. But if you focus on larger scale networks, this greedy algorithm is quite costly because we need to perform the search over a large number of observations. So what we have been able to do is to incorporate random sampling strategies in order to significantly reduce the cost of performing observation using this greedy algorithm. And we have been able to show that this algorithm achieves nearly the same performance guarantee as the baseline. And here I'm just showing a quick application of this to autonomous driving, where we have an autonomous car as different sensors, such as radar sensors and camera sensors. And we have been able to show that by using this observation gathering scheme, we can significantly reduce the runtime of tracking, while at the same time ensure that we have essentially the same tracking error. So for the interest of time, I'm just going to skip this part. But just to mention that the third line of work that I've been focusing on is related to learning representations to perform inference in scenarios where we have access to a limited number of data. And we have been able to design non-convex optimization problems, and in some cases, we are able to drive performance guarantees for them. And we have been able to show that these optimization problems that we have developed have applications to, for instance, computer vision, real-time motion segmentation, or tracking water masses in the ocean, or even the study of genetic variations in genomics. So with that, just 1 minute about the work that I'm going to do in the future. So far we have been mainly focusing on offline problems. And what I'm going to do is to consider scenarios where there is uncertainty and there is a dynamic environment, and we need to be able to deal with the heterogeneity in these problems. So we have some prior works, but my goal is to continue in this direction. And finally, we have been mainly focusing on what I call this performance-oriented mindset, but there are other aspects such as robustness and privacy that we need to take into account. And again, we have some existing works that in the future I'm trying to expand on that and build upon that to sort of enable that not only we have efficient algorithms for collaborative learning system, but also we have algorithms that are private and robust with respect to, let's say, adversarial attacks. So with that, yeah, I conclude my talk, and thank you for your listening, and I'll be happy to answer questions.
Thank you very much. So I guess it'll be a little bit over 5 o'clock, but you know, if you have any questions to ask, you know, any of the presenters today. You know, if you have questions, please feel free to unmute yourself and ask a question, or type in the chat window. And if not, you know, since it's Friday, so we could end our panel. But before ending our panel, I really want to thank our co-director, Shreya Sandram, who actually have done all the organizational work of this panel. And also thank you to all these presenters. And I learned a lot about especially interesting demos, interesting ideas, and interesting directions. And of course, also thank you to all for your attendance, for your time.
Thank you for having us.
Thank you.
Thank you. Thank you, Joshua. Thank you, Shiraz. Yeah, thank you, everyone.
Take care.
Okay, all right.